Yes. Welcome back to the post-lunch session. So this session will be chaired by Iclaa sir. So over to you.
Thank you. So welcome back. After lunch, I know you will feel sleepy, but we have three beautiful talks which will keep you awake. So the first speaker is Professor K. Siva Subramanian from IIT Bombay. So what do you?
Hello. So firstly, before I start, I'd like to thank the organizers for their kind invitation. So I've come here to Manipal so many times that actually the number of fingers in one hand is not sufficient. So it's definitely more than 5, but it's less than 10. So the 10th one I will announce, yeah, because 10th is a milestone for me. So I've come here, maybe this is my 8th, if my memory serves me correct. So I have a counter. So, and it's every time, no, it's no mean feat to just come here and expect things to work, and it does. So again, I'd like to thank the organizers for wonderful organization. So, as Professor Rafiqul has mentioned, see, holding your attention just after lunch is not going to be easy, but I have an escape route. If you don't pay attention, I'll blame it on the schedule. If you, of course, pay attention and ask me questions, I'll take the credit. Yeah. So it's a win-win situation for me. So, jokes apart, let me start. So this is, I'm going to talk about unimodality of the coefficients of the characteristic polynomial. Yeah. And what matrix I'll tell you. Yeah. So this is joint work with, they were postdocs at that time. So Rakesh Jana and Ishwar Mahato. Ishwar is here, but he'll talk on something else. Rakesh is not here. Yeah? He has some. Okay. So let me define unimodality of a given sequence. So usually we consider only univariate sequences. That is, sequences are indexed by one index. Sometimes you'll have A and K, in which case unimodality has to be defined differently. So here I have AI, a sequence. So I running from 0 to P or 1 to anything. Yeah, it's a finite sequence. That's all I care. So it's unimodal if you look at the sequence of real numbers, it keeps increasing. Maybe it stays the same at some point and then decreases. Yeah. So unimodality is increasing and then decreasing. So for example, if you look at binomial coefficients, there are some examples given. I'll define log concavity in a minute. If you look at the binomial coefficient, see, we know that n choose I keeps increasing till n choose n by 2. N by 2, we have to be careful because it can be fractional. And then it keeps decreasing. Yeah. And it's symmetric also. Yeah? Similarly, Stirling's numbers. So these are all taught in the first course in combinatorics. So Stirling's numbers of one kind is when you count permutations by number of cycles. Yeah. So Stirling numbers of the second count is when you second type you count set partitions by number of parts in the set partition. So don't worry, these are just some examples. So what I want to give you examples of sequences which keep increasing up to some point and then decreasing. So sometimes sequences are symmetric, in which case the maximum will be at the middle, but it need not be. Sometimes you can just have a sequence. No, if you are having a general definition of unimodality, it can keep increase maybe up to 2n by 3 and then decrease. Maybe increase up to n by 3 and then decrease. Anything is possible. Maybe the constant sequence. There, everything is a maximum. Yeah, so that is possible. So I've given you 4 instances, Eulerian numbers. That is, you count permutations by either descent or exceedance. There are standard examples, and I'll call a sequence to be log concave if you look at AI squared. So you take AI squared and you compare it with AI minus 1, AI plus 1. So because I want this AI minus 1 and AI plus 1. So maybe I should have said, if you have 1 to P, I should have said I is between 2 to P. Yeah, 2 to P minus 1, because you want the previous term and the next term to. Then log concavity, AI squared is bigger than AI minus 1, AI plus 1. So log concavity will be abbreviated to LC just for the purposes of this talk, and unimodality by capital U. Yeah, just for. And all these 4 examples, standard ones, they are both unimodal and log concave. Yeah. But binomial coefficient, it's remarkable. There are good proofs. You can give it in your class. How to show they are unimodal is easy. Log concave, you can get a bijection. Take a set of size k, take 2 copies, yeah, and set of size k plus 1, set of size k minus 1. Can you get an injection? If you get an injection, that means you can show. So there are combinatorial proofs, there are non-combinatorial proofs, there are quite a few things. So I'm going to be talking about unimodality and log concavity of a sequence of real numbers. Yeah, where are these real numbers going to come from? They are going to come from the characteristic polynomial of some matrices. Yeah, for me. So even though we know somehow it is unimodal or log concave, the location of the peak, that is one. There is some point. It may not be. Sometimes maybe. So the location of the peak is what I want to. At what index? Maybe it is at a sequence of length n. Maybe it's at n by 2. Maybe it's n by 3. Maybe it's n by 5. We don't know. We have to figure it out. So we will look at the characteristic polynomial of some distance-related matrices. I'll tell you what they are. And so there is, again, if you look at books which define characteristic polynomials, there are 2 variants. They'll say determinant of xi minus m or determinant of m minus xi. It doesn't really matter. But for me, I'll fix this because then the characteristic polynomial is always monic. If you say determinant of m minus xi, depending on the order, sometimes it will be monic, sometimes it will be in the coefficient of x power n will be minus 1. I don't want that. I always want my polynomial to be monic. Of course, you can multiply by minus 1 later. But to ensure that there is no such problem, always my characteristic polynomial will be monic. Yeah, just for that purpose, I've defined it to be determinant of xi minus n. Yeah, and we will set this m to be either the distance matrix of a tree, and I'll tell you why tree is studied often. And because it's a distance matrix, so what does it mean? I have a tree or a connected graph in general, and then vertices are labeled 1 to n. So you have an n by n matrix. Rows are also labeled from 1 to n. Columns are labeled 1 to n. Row I, column j, what is the entry? The distance from vertex I to vertex j. Yeah, that is the ijth entry. Yeah, and why do we study this? Because the graph is connected. This distance is a real number. It's in fact a non-negative integer. Yeah, it won't be infinity. So if the graph is disconnected, you may get some infinity in trees in your distance matrix, but you will not have that. And tree is a minimally connected. That is, if you remove any edge, it ceases to be connected. So that's why it's studied in this. And there are a lot of interesting results studied about trees. Yeah. So if you look at the distance matrix of any connected graph, what can you say about the diagonal entries? So distance from I to I itself. So if you're already at I, you don't have to go to any other vertex. So the distance there is always 0. Yeah. To go from vertex I to vertex I itself, how many edges do you have to traverse? 0. So what is the minimum? 0. Yeah. And so the trace of this distance matrix will be 0. Yeah. And very easy. All of you will know, I'm sure, that the coefficient of x to the n minus 1 in the characteristic polynomial will be related to the trace. So that's why the coefficient of x to the n minus 1 will be 0. So here is an example. So let's call the coefficient of x to the k in the characteristic polynomial as ck. Yeah. So I'll fix a distance matrix D, and I have 2 examples here. So this is a tree on 7 vertices, another tree on 6 vertices. Tree on 6 vertices is very clear. That's the path. This is some other. I just chose some. Yeah. And as we've said, the characteristic polynomial is always monic. Yeah. So if you look at T7, the coefficient of x to the 7 is 1. So I don't want to string it as a polynomial because firstly it beats the length of the slide. Yeah. That is one thing. And secondly, it's easier to compare like this. So the characteristic polynomial is monic. So coefficient of x to the n, the largest exponent, that will be 1. So because it's a tree on 7 vertices, coefficient of x to the 7 will be 1. The P6 is a tree on 6 vertices, so there's nothing here. Yeah. So this will be 1. And as we have said, why is this 0? Well, this is the trace of the distance matrix. Yeah. So this 1 and 0 can be figured out. All the others they happen to be negative, at least in this case. Why so? So one has to see. Yeah. And can we do something? Yeah. Are they unimodal? So here we have a sequence of real numbers. So they are firstly negative. So suppose you take the positive, you take absolute value. So it is 105, 448, 648, 384, 80. So you take absolute value. So first point here, see the 1 and 0 are easy. You can ignore these two. These first two coefficients you ignore. So the first term in my sequence is 105. I have taken absolute value. Then 448, that's increasing. 648, more so. Then 384 is decreasing. 80 is decreasing further. Likewise, this you take 120, then 752, 1840, 2080, and then decreasing. Yeah. So this seems to be a pattern. Yeah. So this is the conjecture of Graham and Loash. It's a theorem now. So there are so many, Alipur, quite a few people, they proved this. So actually the conjecture says something about the normalized coefficients of the characteristic polynomial, and I'll tell you what it is. Yeah. So what is the difference? So you take Ck, as we noted, this minus Ck seems to be positive. Yeah. So you take minus Ck and you normalize by 2 to the n into and 2 to the k minus 2. So I've got the things here. Yeah. So 2 to the n, so 2 to the n minus 2 I'll take. So it's 2 to the, so you're dividing, firstly I'm doing minus, I'm multiplying the Ck by a negative, and I'm also dividing by 2 to the n minus 2, and I'm multiplying on the numerator by 2 to the k. That's all I'm doing. Yeah. So you just check what this happens here. So this, because of that multiplying by this factor, 120 is 120. This will become divided by 2. It will be divided by 4, divided by 8, so on. Yeah. So you get this other sequence. And what they showed is that this, take any tree, look at the distance matrix, look at the characteristic polynomial, look at their coefficients, you do this slightly scaled version. Yeah. That is, you are multiplying these by negative and then the others, and you get, yeah. And they say only for 0 to k from 0 to n minus 2. So the n minus 1 and n are not, we don't really care. Yeah. So these two we don't care. Yeah. So that's why I just left it as this. I should have done something else if I were to do that scaling. These two terms you ignore. Yeah. They're not relevant. From 0 to n minus 2. That's the sequence that we consider. Yeah. So that sequence is unimodal and log concave. Yeah. This is what they proved. Nice result. And for the proof, no, they use real rootedness of the characteristic polynomial. And this is kind of straightforward. Why is the characteristic polynomial real rooted? From spectral theorem. Because the matrix is real symmetric. So the characteristic polynomial will have only real roots. So that is needed to show log concavity. In fact, there's a lot of study about log concavity. You look at the polynomial as real roots, the coefficient divided by n choose k, the polynomial of degree n, you look at the kth coefficient divided by n choose k, that is it itself, that sequence is log concave. There are quite a few interesting results, and this result is due to Newton. So it goes back to a long time, and lots of ideas and results we know about log concavity. And for unimodality, we need, so I said they are both unimodal and log concave. So for the log concavity, we need real rootedness. To prove unimodality, we need this result, yeah, which Heidelberg, Gary, and Graham, which says that the Ck is negative, yeah, which if you look at it, yeah, the Ck is negative, yeah, when k is between 0 to n minus 2. Yeah, for k between 0 to n minus 2, Ck is negative, and hence for us, no, yeah, the dk will be positive because we have defined dk to be minus of Ck, and what you're scaling by is not going to be negative, it's a positive. So dk will be non-negative. Okay. So where is the peak of these scaled unimodal coefficients? So now that we have somehow this, due to some theorems that we have put together, we know that you take the characteristic polynomial of the distance matrix of a tree, it is unimodal and log concave. Yeah. And this is just, we've done some scaling. Yeah. Where is the peak? Is the peak unique? See, sometimes you look at binomial coefficients. Is the peak unique? So if you say 1, 3, 3, 1. So 3 choose 0 is 1, 3 choose 1 is 3, 3 choose 2 is 3, 3 choose 3 is 1. So there the peak is not unique because peak appears at. So when n is odd, these binomial coefficients, they have no unique peak. And in fact, there is this, for those who, if you go to the first, yeah. If you look at this, no, the Stirling's numbers of the second kind, there is a remarkable result which says that this sequence of Stirling's number of the second kind is unimodal. But which is the peak? We don't know. We have, all we know is there's a theorem of Canfield which says peak occurs at either one index or the next. Which of the two is the peak? We don't know. They've narrowed it down to it can be either this or the next. So there is, if you look at this, you start digging deeper, there are lots of interesting results. Finding the peak is not going to be easy. Yeah. So where is the peak? This is what we want to find. Yeah. Yeah. Where is the peak? Yeah. Is it unique? Yeah. So even this has been studied, and I'll tell you. Yeah. So first point is, see, if you normalize the coefficients, so there's a typo there for the coefficients. Sorry about it. You normalize the coefficients. That's not important for unimodality. Why? Because if your sequence is unimodal, you divide it by some 2 power k or 3 power k, alpha power k. It will still be unimodal. Why? So that's a, because you are scaling the coefficient of the characteristic polynomial alpha power k, your alpha is a positive real number, it's still okay. Yeah, this is a remark in their paper and it's not so hard. Yeah, this is one thing. First thing I want to mention is, if you normalize the coefficients for unimodality, it doesn't really matter as a general theorem. To find the peak location, of course, it matters. Now, if you scale down, now the peak location might shift after you do some normalization. So there you have to be careful. Yeah. So whether you take the normalized version or the non-normalized version, that is important to determine the peak location. Okay, that's the important. So I will anyway consider only the coefficient of the characteristic polynomial without any normalization for this purpose of this talk. Yeah, because that is easy to state all results. Yeah, this manner. Yeah. So what they did was show that there was log concavity and unimodality, and there's a conjecture about the peak location that's false actually, but we still don't know. For arbitrary tree, where is the peak location? We don't know. Yeah, and some others, they have recently 2024 they have extended it to the characteristic polynomial of distance matrices of block graphs, or not trees, but to block graphs. Yeah. So they give similar things, and they here finding peak location again not straightforward. Yeah, they give bounds. Yeah? Peak location. Yeah, that's all. Yeah. So anything till now? Because then I'm going to go to some other. Now I'm going to define two more matrices, and then so now is this part here? This is like the brief introduction that I wanted to say about unimodality and log concavity. Is this okay? Any questions? Ask me now. Yeah, because I know I have a hard task post lunch. First talk post lunch. But any questions now? Please ask. Yeah, I know it's a good point. Just to, yeah. Any, if there are no questions, yeah, we'll go on. So I'll consider this 4-point condition. I am going to define two matrices. To define the two matrices, I need this condition. Yeah. So there is a good condition to check whether a given distance matrix, no, does it arise from trees? So this is a standard problem that people in biology face. That is, people who do study. So this area of biology called phylogenetics. So they are trying to somehow they measure distance between, let's say, two virus or two types of monkeys. Yeah, and then they maybe DNA similarity something. Yeah, so they have a distance between two species, and then in general they believe that this evolution, no, you want to know which species gave birth to another species. Some viruses mutate and form new viruses. So what is the tree structure on set of all viruses? This is what we want to find. So we have some distance between them, yeah, by looking at some laboratory data. And why is there an underlying tree in the background? That's, we believe that nature evolves in a tree manner. That is, there is some species, it mutates, then there is something which mutates. There is no back loop. This will not go and give you back another thing. That we don't believe. Yeah. So why is that so? That this is what biology. All the biologists I've known, I've asked. They say it's obvious. So I mean, what is the proof? Then it's obvious. So let me also say, if you want to figure it out, yeah, you can spend some time on it. But from whatever I've spoken to all my friends who know biology, for them it's obvious that the process of mutation is a tree. There's an underlying tree behind it. What is the tree that we don't know? So in this, if you are given distances, so coming back to the problem, you are given a set of, let's say, viruses, 10 of them. You want to know the underlying tree, which gave birth to another, which mutated and gave birth. This is what you want to find. The underlying tree is what you want to find. So firstly, is it coming from a tree or is it not coming from a tree? That's the first question, no? We have some data. Then that's like a distance. And these satisfy triangle inequality, they are symmetric. The distance between two species of virus will be symmetric. Say distance between pairwise distance. So is it coming from a tree? That is a good question to answer. That's a good question to ask, and hence that is studied often. And here is a remarkable theorem. Yeah? It's an if and only if characterization of distances coming from trees. Remarkable. Yeah. So you take these three, you take 4 points. You take so dpq plus du. Since you know the distance matrix, you know all these quantities. So you take 4 points. There are 3 perfect matchings. So you take some of these perfect matchings. So dpq plus dvu. So I've given the perfect matching in different color just so that it makes life easy too. And here dpu plus dqv. And the green one is dpv plus dqv. Okay. So you take 4 points. Either it is this sum of this distance plus this distance. That is one of the choice. Sum of this vertical plus this another choice. This cross plus this curve, the other choice. So you take these 3 terms. So given any 4 points, you can get these 3 terms. And this 4-point condition says that the maximum should be equal to the second maximum. If that happens for all choices of 4 points, then this distance comes from trees. Otherwise it doesn't. Is the statement clear? You want to know, you're given a distance matrix. Does it come from a tree or does it not come from a tree? That is the question. What is the answer? You look at any set of 4 points and you look at these 3 terms that you get. Yeah, as I've said. From these 3 terms, maximum is equal to the second maximum. Then for all choices of 4 points, if that happens, then the distance matrix arises from a tree. Yeah, that's the point. The result is due to this person called Buneman. So is a tree, if it is connected, has no triangles and has distances satisfying the 4-point condition. And the converse is if D is a metric that satisfies the 4-point condition. So there is a weighted tree. So the reason why they say this second condition has a little more complicated, because if you take any distance matrix, you take a principal submatrix. That is also going to be a distance matrix arising from a tree. So that to take care of that, he says the weighted tree which contains the elements of S among its vertices. Yeah. So this is the okay. So I will define 2 matrices. Both of these will be starting from a tree. So I'll start from a tree on n vertices. Its distances will have to satisfy the 4-point condition because of this first theorem. The tree if and only if. Yeah. This first theorem, Buneman has 2 theorems. The first theorem that I am interested in tells you that if you start with the tree distances will satisfy the 4-point condition. Okay. So you look at these. I'm going to define an n choose 2 cross n choose 2 matrix. So rows and columns are going to be indexed by pairs, unordered pairs of vertices. Yeah. So you look at the row indexed by ij and the column by kl. Yeah. So row indexed by 2 vertices I and j, column by k and l. You look at these 4 terms that arise. So I should have called ij kl. So these pq are wrong. Huh? Should be ij kl. Yeah. There's a mistake here. This should be ij kl. Likewise. Yeah. I made a mistake here. So now I define 2 matrices. One is max. Look at the maximum entry in that among those 3 terms. So 3 terms, one is this sum of this plus sum of this, that is 1 term. Sum of this plus sum of this, second term. Sum of this plus sum of this is 3rd term. So among these 3, which is the maximum that you put in you define the max 4-point condition matrix associated to the tree T in this manner. Likewise, you associate the min 4-point. In this, you take the minimum of the 3 terms. Yeah. And both these are studied. I'll give you an example. So here is a tree that we start on 5 vertices. So because I'm saying it's an n choose 2 cross n choose 2 matrix, the matrix will have 5 choose 2 is 10. Yeah. So there will be 10 rows, 10 columns. And let me illustrate. Row 1, 3, column 4, 5. So 1, 3, column 4, 5. So what are the 3 terms? 1, 4 and 3, 5. Distance will be 2 plus 3, which is 5. Well, one of the terms there. 1, 5, 3, 4. Here again the distance is 3. The distance here is 2. So that sum of the 2 plus 3 is again 5. And 1, 3 and 4, 5. So 1, 3 is 2. This is 1. So I will give you 3. So is it clear? So there's 3 terms there will be 3, 5 and 5. And you can see max equal to second max. Yeah. And of course, see 1, 3, 4, 5 same as 4, 5, 1, 3. The matrix has to be symmetric. Yeah. The other thing is there's some redundancy. 1, 3, 4, 5 is same as 1, 4, 3, 5. If you look at 1, 4 and 3, 5, what are the terms coming there? Again, you'll get the same set of 3 terms. 1, 4 and 3, 5. Whether you choose 1, 3, 4, 5 or you choose 1, 4, 3, 5, the 3 terms you get will be the same. So you will get the same thing for the min 4PC. Here I am trying to illustrate the minimum 4-point condition matrix. And likewise 1, 5, 3, 4 will also give you. So apart from redundancy due to symmetry, there is extra redundancy. So you can't expect this matrix to be full rank. Yeah, this is what I want to say. So here is another. Sometimes it may happen that the 3 terms are all identical. Max equal to second max, but maybe all of them are same. That is also possible. And I'm giving you an example. It's possible. Okay. So this min 4-point condition matrix that was studied by Bapat and myself, and it has rank n. You can get a basis So n meaning, see, all the rows are indexed by subsets of size 2. So every edge is also a subset of size 2. So every edge, there are n minus 1 of them. Any tree on n vertices has n minus 1 edges. This is a standard theorem that we study on trees. And then you take one non-edge. Yeah, f is any non-edge. That is also good enough. Yeah. So determinant of that, and we take f to be such that the endpoints have distance 2. The endpoints have distance k, you will just get a factor of k here. Yeah. So determinant we have found out. In fact, it's independent of the tree. Yeah. And the Smith normal form also we found. So this is a result of Bapat and myself from 2020. And so we now try to find out. We have this basis B. You look at the min 4-point condition and you restrict it to the rows and columns in our basis B. So that's a full rank matrix, n by n. And you look at the characteristic polynomial of this matrix, the min 4-point condition matrix, but restricted it to the rows and columns of the basis that I have described. Yeah. So I am saying take all the edges in your tree and take one non-edge which is at distance 2. Yeah. That is my basis. Any such basis, because the choice for the last term is not unique. But no matter what basis you take, you will get this to be the determinant. And no matter what basis you take, so what we say is, as this k varies from 0 to, I've made mod k and I'll tell you why. The next result will be even more technical. There, and I can tell you what I have to multiply by, but it becomes n minus p, the factor, minus 1 to the n minus p. I'll tell you. So to make life easy, I just take absolute value of the sequence of the coefficients of the characteristic polynomial. So this is unimodal and log concave. So again, unimodality, somehow you have to do log concave, it follows from real rootedness. So one real rootedness is there, that's easy. And here we can tell you also where the peak is. So the peak, I'm not able to tell you exactly, but like I said for the Stirling's numbers, the peak lies around n by 3. So you see n minus 2 by 3 less than the, so if t is the index where you get the maximum, t is roughly n by 3. If you're okay with roughly, it's very good. Otherwise, I'm telling you exactly, it's between n minus 2 by 3 and n plus 1 by 3. So we have narrowed it down to almost, no? This can be, what is the length of this t? It's either some fixed number or 1 plus. There, which of the two is maximum, we also not able. We are not able to pin it down for all trees. For some trees, it turns out to be the left one. For some trees, it turns out to be the right. I don't know. So I don't know. We are unable to pin it down for all trees. But I'm telling you, take any tree on n vertices. Where is this peak going to occur? So this is the peak for the non-normalized. That is, just take the coefficient of the characteristic polynomial. That's it. It is log concave, unimodal. Where is the peak? Around n by 3. Where n by 3, so n minus 1 by n minus 2 by 3, n plus 1 by 3, it's almost there, n by 3, it's almost. But that's all you could do. Yeah. So this is the first thing I wanted to say. And I have another. So I'll tell you a little more about the proof. So there is a survey by this Peter Brandon, which is very good. Yeah. If you want to study something on log concavity and unimodality, there is this good survey by Peter Brandon. And it's a folklore result that you take a real rooted polynomial with sequence, the coefficient sequence is log concave. If it is positive and log concave, then it is unimodal. Yeah, but if the sequence has negative terms, it won't work. Yeah, all the coefficients have to be positive. And if they are log concave, then it is unimodal. This is the standard result that we know. And so if you take the characteristic polynomial of any matrix, if all the roots are positive, so if all the roots are positive, what can you say? The coefficient the polynomial will be like x minus a1 into x minus a2, etc., x minus an, where all the ai's are positive. Will it give you coefficients which are positive? Can't say. Whereas if all the roots are negative, then it will be x plus a1, where a1 is positive. I am saying x plus a1. So the root will be minus a1, yeah, and a1 is positive. So x plus a1 into x plus a2 dot 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 x plus an. What can you say about that? All coefficients will be positive. So that's good. So the first part of this lemma 8 is trivially true when the first part anyway is true, log concave, because it's you want it to be real rooted. Real rootedness anyway we get. All matrices are symmetric, so they are real rooted. Yeah? So the first part is there is nothing to do. When the eigenvalues of m are all negative, then by what we just saw, x plus a1 into x plus a2, etc., that will tell you that the coefficients are all positive. So then you can apply the second part also. So if all eigenvalues of M are negative, that is quite the opposite of positive semi-definite. Now I want it to be negative semi-definite. Yeah. Then we are done. Yeah. So if M has exactly one positive eigenvalue, so many of these matrices that we consider, they have exactly one positive eigenvalue and the remaining are all negative. So if all are negative, so for you, the coordinate axis, maybe y, so one positive, remaining are all negative. If all are negative, is very good. 5 minutes there.
3 minutes.
3, okay, I'll finish. Okay, so if all are negative, we are done. Many in our case, we'll get one to be positive, others are all negative. Then we have to do some extra work. That's what we have to do. Okay. So the main point is this. Exactly one positive and the remaining are negative. Then we can still do it. Yeah. So what I do is we generalize it to the case when number of positive eigenvalues will be 1. Yeah. So maybe with this, this is the main result. Maybe I'll let it go because the inertia I want it to be 1. That is the number of positive eigenvalues is 1. Then the remaining are negative. Of course, there could be some zeros. That's okay. In that case, we get this result. And maybe I think this is good enough. Yeah, I'm almost. There's another thing about the Steiner distances. Maybe I will do the Steiner for another time. Instead of trying to go on to the Steiner, maybe I'll explain this in just the last minute. So the main point here is if all your eigenvalues are negative, so here is your coordinate axis, here is the y-axis. If all are negative, we can apply the folklore result. But unfortunately, in our case, not all are negative, one will be positive. Still, we can manage to. Now, what about 2 are positive? We don't know. So you can, just like we go from all negative to 1 positive, we could do something. So maybe because we have 1 positive, can you do 2 positive? Then can you do 3 positive? No, we don't know how to do. So we are stuck there. From going from 1 positive, remaining all negative eigenvalues, to 2 positive, n minus 2 negative eigenvalues. That itself will be a remarkable progress, in my opinion. We don't know how to do it. We are stuck. So any ideas any of you have, it will be good. So my slides are anyway there. If anybody wants, I can anyway send them to you. I have one more example metric, but that's okay. Yeah. So this is about some Steiner distance, and here we don't even have a guess for the peak location. See there for the first matrix we had said it's about n by 3, roughly n by 3. Here for the another matrix, we can show that it has 1 positive and remaining are all negative. So by applying the earlier thing, we'll get something. This is the second matrix. I have not described the matrix. Yeah, sorry, I don't have time. But at least, from the general theory, you can believe that it has. Okay, so suppose it's unimodal and log concave. Where is the peak? We don't know. So we only know for the star when the number of leaves is large, we are able to do it. The number of leaves is small, like path, hopeless. I don't know. Peak location varies. It jumps here and there. And there's some data, but I'm not able to see a pattern. I'm not able to conjecture. I don't even have a conjecture to me. Yeah. If I have a conjecture, I can state it with some confidence, and maybe somebody can do something. I don't even have faith in the data. From the data, I'm not even able to see a pattern and offer a conjecture. So something may be there, but I don't have. Yeah. Whereas in the previous case, this is the second matrix. The first matrix, I can tell you is roughly n by 3 for all trees, no matter what tree. Take a tree on n vertices, peak is going to be n by 3 roughly. Here, peak is there, but yeah, where? I don't know. Yeah.
We have time for one quick question or comments. Anyone? No? Then let's thank the speaker for a very beautiful and lively talk.
I request Rafiq sir to honor our speaker. Thank you, sir. Thank you, sir.
So our next speaker is Professor Lina Melozzi from University of Naples, Federico II, Italy, and she'll speak on bimatrix games having pure Nash equilibrium. Professor.
Thank you. Oh. What was the code of? So, thanks to the chairman for the introduction. But first of all, it's really nice to be here, and for that I want to thank a lot the organizers of this such beautiful conference, and for the possibility for me to be here in Manipal. Thank you again. My talk, as you see, is framed in game theory, so maybe it's a little bit out of the scheme of the main goal of the conference, but it's strongly related, as you will see. I will introduce some notation. It's maybe you are familiar already the biometric games. It's I mean a scheme that we use in game theory, and it deals with metrics. Then I will shortly introduce the solution concept that I'm going to achieve. And finally, I will present the existence results that we prove, because this is the aim of what I want. I would like to have equilibria. And a few words about this. All the talk is based on a joint paper with Professor Naga Krishnamurti. This paper has been published in International Game Theory Review recently, and I like to precise the story of this paper that we dedicated to the late Professor Tiru Parthasarathi. The paper was inspired by him. We had the occasion to speak during lunchtime in Delhi during one of the beautiful conferences that Professor Nyogi organized in January. And so just I asked a question to Professor Parthasarathi. Naga was close to us. And so we started to discuss about a possible connection between some results from the linear algebra and some classes, special classes of games. And so we started mainly Naga and I to work on this, and it was bad that Professor Parthasarathi passed away before to see the final result, but we dedicated to him this work. So just for those of you, I think a few people who are not familiar with game theory, I focus on this. First of all, I will consider finite games, and this is the typical notation of a two-player non-cooperative game, where x and y is, as you see, natural numbers, and sim states for the possible choices of each player. X for the first player, Y for the second player. So that's why it is a finite game. We call these numbers also pure strategies because, as we will see, it is possible also to deal with mixed strategies, but this is philosophically different. And I strongly point out that in our work, in our paper, we look for pure strategy equilibria, because it depends on the framework. If you deal with applications, it is fundamental to have pure strategy equilibria because you have to know which is the best choice. If you deal with a financial problem mainly, or some engineering, some models from engineer where you repeat the phenomenon that you are studying, and maybe you can estimate the frequency. In that case, it is possible also to deal with the mixed strategy in the sense that they are probability distributions on the pure choices. These are totally different and depend on the context, but I insist that we deal with the pure strategies. And so we call this a biometrics game. I mean, it's a matrix, and with the n row and n columns, and each entry is a pair. And the pair is fundamental, and it's an ordered pair because the first component is the profit of the first player, and the second component, the profit of the second player. And the entry is determined by a row and a column, and the row is the choice of the first player, the column the choice of the second player. So in a sense, you have two functions, a and b, defined on the Cartesian product x times y, and these two pairs, two functions, give you the profits of the players. So you can schematize in this way. You can see the different colors because blue is devoted to the first player that chooses between 1 and m, and orange the profits of the second player that chooses between 1 and n. This is the IAJ entry. It's a pair. This is the profit of the first one, and this is the profit of the second one. So just a few, I have to precise that it is called the zero sum. Maybe this is well known when the profit of the second player B is the opposite of the profit of the first player A. Roughly speaking, if we are two, what I gain is exactly what the other one is losing. This is the zero sum game. And in this case, since what the second player is losing is given exactly by the opposite of my value, it is enough only one number. And that's why we use a matrix. A matrix means m times n matrix, where the entry is just the number aij. That's the profit, let's say, of the first player. Another definition is the symmetry, that is related to the symmetry of a matrix, but not, I mean, in this sense, it's a symmetrical game where x and y coincide, so players choose in the same set, and the profits are in this relationship. Aij is the same of the second player profit evaluated when you exchange row and column. So BJI. This is more or less another idea that we know. Maybe you call it in a different way. I fix a pair of strategies for each player, and I intercept a 2x2 sub game. I call it a sub game. So in red, you see, I choose only this sub game. It's a game where you have the same two players, but they choose in between IA prime and JJ prime. And this is the formal definition of a subgame. So for the generic submatrix, you have this 2x2 submatrix. If you have a zero sum, I told you it is enough for just one component, and you have this 2x2 submatrix. Now, let's see. This is a game, a two-player finite game. The first player in blue, you see, chooses between 1 and 2, and second one between 1 to 3. And you see if the first one chooses 1 and the second chooses 2, the first one gains 0 and the second one gains 1. I think that all of you see which is the best decision for everybody, and everybody is happy here because if you see, it's evident that 8-8 makes everybody happy. And so the best choice that all we can imagine is that the second player will choose 2 and the second player will choose 2. In that case, both of players receive the maximum 8. That's a good question. So maybe I call this easy case. We can, how can I say, we can anticipate the best choice of both players. Okay, I think that you agree. Now, I present you, maybe this is also something that is well known. Maybe when you were kids, you played to the rock, scissors, and paper game. It's the decision of 3 possible choices. I remember that the symbol of rock is this, the symbol of scissors is this, and the symbol of paper is hand. and you play. I think that everybody did. And the rule, let's say the rule, is that rock beats scissors, and the scissors beats paper, and paper beats rock. Generally, it's two-player game. So this is the possible mathematical description of this game, and usually it is considered a zero sum because when we make the decision, for example, the first player chooses paper and the second player chooses scissors, generally we say that 1 point goes to the second player, but the first player loses 1 point. This is the general rule. And so that's why it is a zero-sum game. I prefer the biometric notation because my question now is the following. What should we expect to happen here? And I think that we experimented this game, at least one in the life. So first consideration, nobody stopped after one right? I think that you have to repeat the game. So maybe we fix, let's repeat 10 times and then we will see. Or maybe other possibility. The idea is that if you consider these biometrics, you do not have any element to say that this choice is preferred to another one. Okay, this is the main point. For those of you who knows the idea of the Nash equilibrium concept, this game has no Nash equilibrium. Okay, so this means that you have other possibility to solve this situation. For example, this is one of the cases where repeating the game, also mathematically you can explain the repetition, because repeating the game you can estimate the frequency, and so that's the probability, and then you go towards the mixed strategies. In fact, it is possible to see that this game has a mixed Nash equilibrium, okay? But this is not the goal of my talk. So I would like now to say, okay, this is the classical situation we have, a finite game without Nash equilibrium, a pure Nash equilibrium. So what to do? Is it possible to highlight some special classes of games, some properties in such a way that you say, okay, this game has this property, so you will find the Nash equilibrium. This is our goal. First of all, historically, the idea of Nash equilibria was published in this 3 paper that John Nash published in between 50 and 53. I recall you that he got the Nobel Prize in 1994 together with Arsani and Selten. In this 3 paper, Nash gave the definition of Nash equilibrium, and also he proved the theorem, the existence theorem for the existence of mixed strategies for finite games. But I do not go into these details. I want to highlight the properties of the Nash equilibria, because it has been formalized by around 2 main ideas. The first idea is the individual rationality. Rationality means that each player maximizes its profits. I mean, if I have a profit and I am rational, I try to choose the strategy that gives to me the best possible. Or if I have a cost, I am rational when I choose the strategy that gives to me the minimum possible. This is the rationality assumption. And the other assumption is the stability requirement. The stability means, this is the key point of the Nash equilibrium, that each player will respect a given strategy profile, assume that A star, J star is a Nash equilibrium. So the player I respect this choice if he is a maximizing choice of one player profit when the opponent is also in that profile. I summarize all these comment in the last sentence. No player wants to deviate from this equilibrium. So if you are at the equilibrium and, for example, the second player say, okay, I don't want to choose J star, I choose J prime. Okay, that player is going to lose profit. This is the idea of the Nash equilibrium. So the formal definition maybe is well known. It's a pair of indexes such that this is true for the first player. So the profits of the first player A is maximum at the equilibrium. And this maximum with respect to the first player, see that this is for every I is the strategy of the first player. But look that the second player is fixed, is at the optimum, is fixed at J star. And a similar situation is for the second player. The second player chooses this B, I star, J star is the maximum for him because this is the maximum look that you maximize with respect to J. That's the strategy of the second player. But look that the first player is stable at the optimum in is I star. It is known that if the game is a zero-sum game, we call it a saddle point. And another definition, the equilibrium is symmetric when, first of all, you need it's symmetric when all the components of the equilibrium are identical. So the player chooses the same. Mathematically speaking, it is important to note that this can be written as a maximum problem. It's the maximum of this function a, k, j prime, j star. J star is fixed and you maximize with respect to k. And in a similar way, the problem of the second player. And commonly we speak about the best reply. The best reply is exactly what the word says. So it's the best way of that player to reply to a choice of the opponent. Let's see in detail. B1 of J, 1 is the best reply of the first player, and the J is something that the player 2 claimed. So player 2 say, I choose J, which is the best possibility of the first player. So I am the first player, this is my best reply. I choose all my strategies that give to me the best possible when the second player chooses J. And so this is mathematically the description. And clearly you have a similar definition for the second player best reply. And please note that the Nash equilibrium is something that satisfies this. Since you have that it is a solution of this couple of problems, you see that call it the equilibrium A star J star. You see that I star belongs to B1 of J star and J star belongs to B2 of I star. Mathematically speaking, the pair I star J star is a fixed point of the best correspondence. Best correspondence is the correspondence defined as the product of these two, okay? And the Nash equilibrium is the fixed point of this map. So going back to the rock, scissors, paper game, I just, for example, wrote the best replies, and it's the underbar, the notation I use. For example, suppose that the first player chooses paper, which is the best reply of the second player. You need to compare in this row, this is the row of the matrix, the second component, because the second component is the profit of the second player. And you have to see which is the best between -1, 0, and 1. And clear the maximum is 1. So the best reply, this is the value, but the best reply is the strategy that gives to the second player 1. And so it's S. So this is the way to read the best reply. But concretely, there is a point here, because remember that Nash equilibria is a pair, and each component is best reply of the other component. And here you don't have the match. So this means, that, and we already said, that there is no Nash equilibrium. These are some comments. Not always there exist. Randomizing is another possibility. It is important to look for pure strategies, and here, for example, in literature, there are many classes already. Well, not so many, but some classes dealing with the games, finite games that has pure strategies. I mean, for such games, you can prove that there exists a Nash equilibrium in pure strategies. So, for example, Mondrall and Shapley defined the potential games in 1996. So this is one of the classes. So our goal was let's try to study in this direction, but there was this starting point. We started from this theorem, and if you see the date is 1964. This is a result by Shapley. Shapley also got the Nobel Prize in 2012 in economics. Shapley proved in that year that first of all, it was a theorem for matrix games, so zero-sum games. And he proved that you take a matrix game, if every 2x2 submatrix has a saddle point, then the entire game has a saddle point. This is, if you see for a moment, a strong result, because it's clear that think about the very large matrices. It's nice to compare every pair of strategies. So the test to see if you have a saddle point is just reported to comparing every pair of strategies. The converse of this sentence is not true, because this is the example that Shapley has. In this game, zero-sum game, this is a saddle point, so the choice 1, 2, so first row, second column is a Nash equilibrium. But if you see the second and the third row, you have a 2x2 matrix game, and here you don't have a saddle point. You can see easily, because this is the profit of the first player, and for each column, the first player has to take the maximum. So the first player best reply is here, but look that the second player gets the opposite of these values. So here you will have 2, so the best reply will be here. So you don't have match, and you don't have the Nash equilibrium between the second and third row. So you cannot say that the inverse of this is true. But we started from this theorem, and the question was, maybe can you extend this for a general biometric scheme? I mean, that is not necessarily a zero-sum game. And so a similar result to this is not true for a non-zero-sum game. This is an example that is in the paper with Naga. This is a 3x3 biometric game, and you don't have a Nash equilibrium in this game, but every 2x2 submatrix has a Nash equilibrium. And for you, trust me, I wrote all the possible 9 2x2 subgames of this biometrics. It is possible to check that here you don't have a Nash equilibrium, but in every 2x2 you have at least one. There are even, for example, this submatrix 2x2. This is first row and the second row. Sorry, first and the second row, and the first and the third column. Here you have 2 Nash equilibria. So it's clear that if you want to generalize the Shapley result, you need to add some property. And so this was the idea of this paper. We have been able to produce 2 types of results. In a first set, we fix, let's say, n by n biometric games. So it's a general non-zero-sum game, but we deal with the symmetric Nash equilibria. That is, again, a refinement of the definition. And in this case, we are able to prove a result in line with the Shapley theorem for a special class of games. But we have also another existence theorem for generic M times n biometrics games. And clearly here you need some assumption. So I hope, how much time do I have? Okay. I don't go into detail, but I hope to illustrate these two types of results that we produce in the paper, and also to leave you with a conjecture. So first of all, I need to introduce this class of games. This is called, I call shortly QH. It's quasi-harmonic, and this is the definition. This is a biometrics game. It's called the quasi-harmonic if for every fix two types of strategies for the first player and for the second player. And you have to satisfy this that I call cross property. The cross property is something that has to be satisfied by the sum game. Who is the sum game? You have a game, you have two profits, first player, second player. The sum game has the sum of the profits, okay? So for each pair of strategy, you consider the sum of the two profits. So the cross property is like this. You sum up these first two addends of the sum game are when you choose ij and I prime j prime. In other words, you sum up the elements of the principal diagonal. Here, with the minus sign, you subtract the elements of the secondary diagonal. This is a 2x2 submatrix. Well, this sum must be 0. Okay, so this is the cross property, and we call quasi-harmonic games satisfying this property. Now, some consideration. If you have a zero sum is the game where if I gain x, the opponent loses exactly x. So I gain x, the opponent gains minus x. So the profits are the opposites, and clearly a zero-sum game is always quasi-harmonic. Second consideration, this is, if you heard about something that helps in the interpretation of this cross property, the sum biometrics satisfy contemporarily these two properties, the property of supermodularity and submodularity. Supermodularity is this. This sum has to be greater or equal than 0. Submodularity less or equal than 0. So in this case, you have both the requirements. If you are not familiar with the supermodularity or submodularity, these are notions introduced in lattices space. And in a sense, they say that they translate the concavity convexity assumptions in the lattices framework. So in a sense, if you want to understand the intuition, it's something that goes in this way. You have contemporarily convexity and concavity. Okay, so this is the submodularity and the supermodularity together. Now this is what we prove for this game. If a biometrics is symmetric and quasi-harmonic, so you have this cross property, then a result similar to the Shapley is true. And first of all, it is possible to prove this. I need another subgame definition that is called the diagonal subgame. So what is the diagonal subgame? I am choosing still two strategies for the first one and two strategies for the second player. And I fix this element and this element on the diagonal. So it's enough to choose I less than j. And so you fix these two elements on the diagonal, and the rest you construct the 2x2 biometrics. But it must be that these two elements belong to the diagonal. In this sense, it is possible to prove that if the game is quasi-harmonic, so the cross property is true, it is possible to prove that every diagonal subgame has a Nash equilibrium problem. So we are in the spirit of the Shapley result. So after this, I go back again on our rock, scissors, paper game because this is the situation. This is a symmetric game. Symmetric game, I recall for you, on the diagonal means that the values of the payoff must be equal. But for example, let's consider RS. So you have the pair 1 minus 1. If you consider the permutation of RS, that means the choice SR, so the first player chooses S, the second chooses R, the profits are exactly exchanged. This is the symmetry in games. So this is a symmetric game. It is a quasi-harmonic because it is zero sum and has no pure equilibrium. So this means that quasi-harmonic is not enough as a property in order to have, okay, you have that some subgame has the Nash equilibrium. I want the Nash equilibrium for the entire game. It is not enough. And so we helped ourselves with another definition that is called the quasi-concavity at diagonal. So let's see the definition in detail. So I consider n by n symmetric biometrics game, and it is quasi-concave at the diagonal if this happens. Consider this is I, J, K, and the K we say is in between I and J. In other words, you'd say, consider that I is less than J. You consider any integer between them, these two numbers. And this is the implication that you have to satisfy. If AJI is greater than AIE, so you are along a column here, then AKI is something that is in between. This is AJI and you have AII. So something in between has to be greater than the element on the diagonal, okay? Now, the theorem that we prove is the following. Now we have a symmetric, okay, quasi-harmonic, and also the quasi-concavity at the diagonal. So we are able to prove that the biometrics game has a symmetric pure Nash equilibrium. So first of all, consider that we prove something more than the existence of a Nash equilibrium, because the fact that it is symmetric, it is not free. A symmetric game may have also an equilibrium that is not symmetric. Okay, so it is not free that it is symmetric. And the rock, scissors, paper game does not satisfy these assumptions because it is not quasi-concave. So this is a set of results, and I wanted to show you that I need strongly both conditions because the two classes are disjoint. Here is the rock, scissors, paper game that is quasi-harmonic and not quasi-concave. Here is an example of a game that is quasi-concave and not quasi-harmonic. Okay, so this is a sort of theorem that satisfies is in line with the Shapley result. But this is not the everything, because this is our first set of results. Now we go in the second part of the paper where we consider a general game. You see now it is not necessarily n times m because we are not looking for symmetric equilibria. We consider a general finite game, non-cooperative. And we prove at first this proposition. So this proposition says that you have to find a row, let's call it the special row, and the name that we gave is H. In this row, something is happening. Every 2 by 2 subgame that intersects with this special row must have a pure equilibrium in that row. This is the assumption that we do. Second assumption, in that row, not all the profits of the second player are equal. If these two assumptions are satisfied, then the entire game has a Nash equilibrium profile. Just a few comments on both assumptions. Clearly, this is the, let's say, row version. It is possible also to give the column version. I mean, if you find a column that satisfies a similar assumption, also it is possible to prove that you have a Nash equilibrium profile. So the situation of the special row is this one. In the game, we see that there is a special row H such that every subgame that intersects this row, so you build the subgame in this way, the H row is this or the other one, and the requirement is that in the H row, you have to see the Nash equilibrium of that subgame. Now, in additionally assumption is that in this row, H row, the payoff of the second player, so this B, must be different. So in this game, for example, there exists a row H. You don't find a row satisfying this assumption, and this game has no Nash equilibrium. In fact, if you see, this is the original game. I built all the 2x2 sub games, and if you check, you need the time. The Nash equilibria is not always in the row that I consider special. So this does not satisfy the assumption of the theorem. And also in this case, the H row is the first one. It is possible to prove that you have Nash equilibria in all the 2x2 sub games, but see that the player 2 has the same payoff, and this game has no Nash equilibrium. It is possible to have a substitute assumption of this. I mean, it is possible to see to avoid, to require that all the payoff of player 2 are equal if you ask that the matrix or by matrix has to have no more row than columns. In that case, we are able also to prove that there exists a Nash equilibrium of the game. So since I have not so much time, I go towards the conclusion, and this is the summary of the general theorem that we proved for the general case. Just I want to point out that looking for the special row, you do not require that every 2x2 submatrix has to have a Nash equilibrium. That is the spirit of the Shapley result. So in this sense, this result is a refinement of the Shapley theorem. So I do not summarize because I have no time. I prefer to go to the conjecture because I have still the rock sister paper game that is in this situation. It is a symmetric, quasi-harmonic, not quasi-concave, and no Nash equilibrium. So this is written in the paper. We wrote this conjecture because clearly it is important to see that at least one subgame 2x2 has no Nash equilibrium. So the conjecture is the following. Maybe it is true that symmetric and quasi-harmonic bimetrics, where every 2x2 subgame has a Nash equilibrium, for the entire game. We are working in this direction, but it is still open. So these are the essential references that I mentioned in my talk. Historical references, the Shapley paper, Monderer and Shapley, the potential games. This for the quasi-concavity notion. And here are two papers by Professor Partassarati and co-authors dealing with the mixed strategy existence. And this is the part for the symmetric Nash, but if you want the complete list is on the paper that is published in International Game Theory Review. And if you want to contact me, I have many addresses because I am a coordinator of a master degree program. You can write to both, but Malozzi Unina is simpler, and you can contact me for any case. Thank you so much.
Any questions, comments?
So you have given whatever literature you have given, no? So that's the exhaustive one.
Sorry?
So whatever the literature you have just referred,
Yes.
so that's the exhaustive one, or there is something else also.
Oh no, this is the one that I mentioned in the talk. In the paper, you have more than this.
But is there any way, that better way that we can identify whether there is a pureness equilibrium? So that
Better.
computationally.
Better is a big
Computationally,
yeah,
quicker
big
way.
word. But we are moving on this because this 2 by 2.
You are looking at 2 by 2. There are so many, no, that you have to see.
Yeah,
and then
I want to
check
reduce.
and-
Yes, exactly. And I told you we spoke with Professor Ragavan, and he addressed us to this Fekete lemma. I don't know if any one of you knows this Fekete lemma. And we are still discussing on this.
So you're looking at quasi-concave. Is there any quasi-convex kind of thing?
No,
No
no,
concept.
no.
Yeah.
I mean,
I've not read all this that your papers, but I'm aware of this. That I looked at your paper.
In the paper, you have many. In the paper, you have many. And clearly, the computational aspect is missing because you can also argue the computational complexity. For example, if you have to check the diagonal subgames or 2 by 2 subgames, it is possible to study the complexity.
The number is very high.
Yes, 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 yes. That's why we are trying to, yeah, yeah. No, it is a deep, a deep topic.
Or they give analyze some matrix classes, putting all the conditions together, whether that will be easier to.
Exactly,
know.
exactly.
It's a matter of.
Exactly. Symmetric and this, diagonal, or separability of strategies.
Class of matrices.
Yes, yes, yes.
Talk about it.
Yes.
Yeah. And use your results to incorporate there.
Yes.
Arrive at those matrices.
Yeah, but this is why this paper was born, because I was just at lunch with Professor Bartasserati, and I don't know, I mentioned it in the talk, this quasi-harmonic games.
These people have large number of paper on completely mixed games. So pureness, there are not many.
This is another
Another
another point of view, I told you.
Thank you, Professor Malozzi, for a beautiful talk.
Thank you.
I now request Professor K.C. Sivakumar sir to honor Professor Leena Malozzi.
So the last talk of this session will be delivered by Professor K.C. Sivakumar from IIT Madras. So I think so almost, I think almost or exactly 30 years back, I met first time KCS. In fact, there is a personal connection. We belong to the same academic family. In fact, he is my academic nephew. And but I know he likes to give the traditional talk, with chalks and blackboards. It gives beautiful talks. And I have read somewhere says that a mathematician giving a talk without blackboard is like a pianist giving a performance without a piano. But he gives beautiful talks, so I'm sure he'll give a beautiful talk without a blackboard and chalk. What views you would want?
Thank you, Rafiq. It's a bit embarrassing. Let me thank Manjunath for the opportunity. He and his team is remarkable. They are doing this so frequently. We just keep wondering whether we can hold such an event in our institutes. Yeah. Okay. So it's good that Professor Niyogi gave the talk in the morning, where he recalled some of the notions that I will require in my talk. So this is about something that I have been dabbling with really. It's about the role of non-positivity or non-negativity in the linear complementarity problem. Now that is one aspect that I have been interested in for a long time. And so that's what I plan to talk today. I realize that the first two slides have been common for a few years now. So if you have seen it, you can, if you're bored, you can skip those. So the first one is about, first two slides are about invertible M matrices and singular M matrices. The starting point is a Z matrix. Z matrix is a real matrix with off-diagonal entries non-positive. All matrices for me in this talk are square matrices. A Z matrix can be written in this manner, Si minus B. When I say non-negative, it's entry-wise non-negative. So you can write it as Si minus B. You observe that the contribution to the matrix A, the contribution to the off-diagonal entries of A, that contribution comes from the matrix B, which goes with a negative sign. And so any Z matrix can be written in this manner. B is entry-wise non-negative. If there is a relationship between these two, the number S and the matrix B, then you get something interesting. For instance, if S is at least the spectral radius of B, then the matrix A is called an M matrix. If S is equal to the spectral radius of B, we have singularity through the Perron-Frobenius theorem. If S is greater than the spectral radius of B, then it's an invertible M matrix. This notion was introduced by Minkowski, and the name M matrix was coined by Ostrowski, who observed further connections. Minkowski essentially proved this result. He considered applying the finite difference method to certain differential equation, and then he observed that the matrix is a coefficient matrix is a tridiagonal matrix, which has a strict diagonal dominance property. It is a Z matrix with that property, and so it is invertible, and that the inverse turned out to be non-negative. That was the motivation for Minkowski. And so you observe that if the spectral radius of B is less than 1, then the matrix B by S has spectral radius less than 1. And so I minus B by S is invertible. Not only that, it admits this kind of a binomial expansion. And you will observe that such a binomial expansion has each term non-negative. And so the inverse of A, there is a mistake here, the inverse of A is non-negative. And so when such a thing happens, it's called an invertible M matrix. And when S is equal to the spectral radius of B, it's a singular M matrix. Now there are complementarity properties for the invertible M matrix, as well as a class of singular M matrices, which is what I want to recall. Yeah. So I have this set of equivalent conditions for a Z matrix to be an invertible M matrix. This is just a list, a partial list from Berman-Clemens' textbook, the Bhagavad Gita for non-negative matrices. So if you take a Z matrix, then the following statements are equivalent. So you will see that there are statements that relate to purely order conditions, statements that relate to a linear complementarity condition, things like that. So the first one is A is a P matrix. So what is a P matrix? Professor Niyogi's lecture. All the principal minors are positive. That's a P matrix. This is the same as asking for A to be an S matrix, Iwsmga matrix. That is, there exists X positive such that AX positive. And the context for us is A is an invertible M matrix. This is a very general phenomenon, monotonicity, as coined by Collatz in his textbook, Functional Analysis and Numerical Mathematics. So A is a monotone, square matrix, monotone. This is easy to see. The linear equation AX equal to B with right hand side non-negative always has a non-negative solution. That's what this says. And so if you look at it closely, it will be clear that the next condition holds. Condition E and F are equivalent. Some of the conditions are equivalent, some of them are not. For example, if you look at the second condition, the Iwsmga condition, there exists X positive such that AX positive holds even for a singular matrix. The all entries one matrix. So if that condition holds along with the Z structure, then you can show that it's a P matrix or is an invertible M matrix, etc. So that's invertibility statement F. There's a pointer here. There's no pointer. Okay, so look at condition F. Invertibility can be interpreted as, so A inverse non-negative really means that all the columns of A inverse are non-negative. You can rewrite it and say that Rn plus is invariant under A inverse. So that you can extend this notion to a cone, for instance. We will have an occasion to look at that. So if you want to show that a matrix is non-negative, show that the matrix keeps the cone invariant. So this will be an interpretation that we will require. A is a Q matrix. Again, Professor Niyogi's lecture, this concept was recalled. Let's remember what a Q matrix is. This is what you have. The linear complementarity problem, LCP A comma Q, has a solution for every Q. And the LCP problem is what? Given A and Q, the problem is to determine if there exists a non-negative X such that AX plus Q is non-negative and that the complementarity condition, X transpose AX plus Q is 0. Complementarity condition, because the vectors are both non-negative, reduces to term-wise complementarity, component-wise complementarity. And so that's a Q matrix, and slightly differing from the notation that Professor Niyogi used. For me, it will be LCP A comma Q. He used Q comma A. So this is for an invertible M matrix. So the invertible M matrix has the property that it's a Z matrix whose inverse is non-negative. That is the same as saying that A is a P matrix, the complementarity connection, which is the same as saying, of course, that A is a Q matrix. Any P matrix is a Q matrix, but there are easy examples of Q matrices which are not P matrices. For example, again, the all entries 1. The all entries 1 is a Q matrix, it's not a P matrix, not even invertible. The rank is 1. Next, let's look at the case of a singular M matrix, but this time a singular irreducible M matrix. So what is irreducibility here? The underlying graph is strongly connected. So that's the thing that we will have. So if you take a singular irreducible M matrix, then it also has complementarity connection. It also has some kind of a monotonicity condition, which generalizes the monotonicity condition definition of Collatz. So let's look at the case of singular irreducible M matrices. The order of the matrix is always n, then the rank is n minus 1. That's because by the Perron-Frobenius theorem, if you have an irreducible matrix, the spectral radius is an eigenvalue, and you can associate a positive vector with the spectral radius, and the nullity will be 1. That vector is unique. Any other non-negative vector is a multiple of this Perron vector, and so the nullity is 1, rank is n minus 1. In the case of invertible M matrices, there exists X positive such that AX positive. In the case of singular irreducible M matrices, again Perron-Frobenius theorem, there exists X positive such that AX equal to 0. Now, matrices that are listed in the previous theorem or this theorem, each has been investigated for its own right. Matrices that satisfy this condition are called central matrices. You have X positive such that AX equal to 0. Homogeneous equation has not just a 0 solution, but a positive solution. These are called central matrices. So a singular irreducible M matrix is a central matrix. I told you that there is some non-negativity of the inverse. There is no inverse because it's a singular M matrix. So there is something about the group inverse. The group inverse is non-negative on the range of A. The group inverse is not non-negative per se, but is non-negative on a subspace. That subspace is a range space of A. That's condition C, essentially. Condition D is that all proper principal submatrices are invertible M matrices. So this connects it to the previous theorem. All proper principal submatrices, all principal submatrices of order n minus 1 or less, they are invertible M matrices. And monotonicity can also be rewritten as, so there is a more general notion called almost monotonicity. That's what you have here. Ax non-negative implies Ax must be 0. If X is a vector that satisfies the condition that Ax is non-negative, then X must be in the null space of A. There is a little more that one can say, but I don't want to get into that. We call what is called as a trivial range monotonicity for such matrices. A is a Q matrix, Q naught matrix. So this is something that is not very explicit in the literature. So I just wanted to make this a point. A is a Q naught matrix. Again, Professor Niyogi's lecture, we encountered this notion. So what is Q naught? Feasibility implies solubility. If there is a feasible vector, if there is X non-negative such that Ax plus Q non-negative, then there is a vector which also satisfies, along with the feasibility, the complementarity condition. So feasibility implies solubility. This is a more general class than the class of Q matrices. So one asks whether a matrix is a Q naught difference Q matrix. Q matrices are identified by invertible M matrices. Q naught matrices are identified singular irreducible M matrices. Now this is a typical instance of a Q matrix. So feasibility implies solubility. So these two slides are common, but remember that the first one is about Q, the second one is about Q naught. Now, there is a famous result which is used as a sufficient condition. It's a very useful result. It's due to Karamardian. Karamardian's theorem says that if these two problems have zero as the only solution. So what are the problems? See, if you go back to the linear complementarity problem, it is asked, so given A and Q, it is asking if there exists X non-negative such that Ax plus Q non-negative together with the complementarity condition. Now observe that if Q is non-negative in the problem, then you can take X equal to 0 as a solution. So whenever the vector Q is non-negative, X equal to 0 is a solution. So one will ask whether the problem has a non-zero solution. The linear complementarity problem, even for Q non-negative, we want to know whether it has a non-zero solution. Okay. Now in that connection, observe that LCP A comma 0 has 0 as a solution. LCP A comma D for a positive D has 0 as a solution. But if it turns out that 0 are the only solution for these two problems, for some D positive, then Karamardian's theorem states that A is a Q matrix. The LCP A comma Q has a solution for all Q. This is Karamardian's theorem. Now, when you encounter matrices in an abstract result, you won't know what the entries are, but you want to know if it's a Q matrix. So that's where this result is very useful. But it's just a set of sufficient conditions. Now, similar to Karamardian theorem, I think there is something that we should consider as an analog, which is due to Ekambaram and Mohan. Ekambaram will be coming on 18th, tomorrow. So Ekambaram and Mohan, they proved this result. This appeared in Mathematics of Operations Research. This is like a counterpart, in my opinion, to Karamardian's theorem.
I think it was in his thesis also.
It was in his thesis also, yeah. 1978 paper. So this applies for the singular case, especially rank n-1. So take a matrix of order rank n-1. If it has a left positive null vector, right positive null vector, then it must be a Q naught matrix. So if the matrix A has the property that it has a positive left null vector and a positive right null vector, rank n-1, it has Q naught property. Laplacian matrix of a connected graph is a typical example. The Laplacian matrix of a connected graph is a singular irreducible M matrix. And you can see that this property holds on, so it's a Q naught matrix. The Laplacian matrix of a connected graph is a Q naught matrix. An application. I mentioned this before, but I just want to underline. A singular irreducible M matrix is a Q naught matrix. You can appeal to this Ekambaram-Mohan theorem to prove this statement. So we have the invertible case, we have the singular case. There is a general theorem which applies, Karamardian theorem, which gives a set of sufficient conditions for a matrix to be a Q matrix. There is another theorem which is not much well known, not much well used. That's the theorem of Ekambaram and Mohan. That's for Q naught matrices. Okay, now what I want to do is to expose you to some sporadic sprinkled results here and there, and then asking whether some counterparts are true or not. So for instance, there is this closure property for the Q0 matrix. If A is a Q0 matrix and if it is invertible, then A inverse is a Q0 matrix. This result is true for Q matrices. One can prove it by using the principal pivot transform, which was introduced in Professor Niyogi's lecture. So a non-singular matrix has Q property if and only if the inverse has Q property. This extends to the more general class of Q0 matrices also. The question is, you know what the Moore-Penrose inverse. So what happens in the singular case? You ask this question. Does the Moore-Penrose inverse have this property? So if A is a Q0 matrix, does the Moore-Penrose inverse also share that property? So I have been able to show that that is not true. This is an example of such a matrix. This so you know what the Moore-Penrose inverse, right? If you have the equation Ax equal to B, it pays to look at A dagger B. A dagger is the Moore-Penrose inverse. A dagger B tells you complete information about Ax equal to B, meaning that A dagger B is the least square solution of the least norm that is of corresponding to the equation Ax equal to B. It is in general not a solution of Ax equal to B. So the Moore-Penrose inverse and the group inverse both are not Q0 matrices, but this matrix A is a Q0 matrix.
So do you have any other example? Because this is a G matrix and G matrix.
I don't.
You can make
I'll try that. See, we are looking at counter examples, and so you get lucky very rarely. But I'll try. Yeah, this is a Z matrix is a Q0 matrix trivially. Yeah, but see, proving that a Z matrix is Q0 also invokes the least element theory. So I won't consider that as a trivial result. But I have another proof that it's a Q0 matrix. That if all entries are negative, then the matrix must be a Q0 matrix. All entries are negative. Even if one of them is zero, it may not be a Q0 matrix. And how does this follow? It follows from the fact that the linear complementarity problem is feasible if and only if Q is non-negative. And so you can go back to this situation. When Q is non-negative, you can take x equal to 0 as a solution. And so in this case, if it's a negative matrix, then it's a Q0 matrix. We also have another kind of a situation. You have a non-singular matrix with the property that the inverse is non-positive. This time you allow for some entries to be 0, but it's the inverse which is non-positive. Non-singular matrix with inverse non-positive, then it is not difficult.
But one thing, singular matrices are never investigated by any one of us.
Yeah.
So in that sense that this result is some addition.
Yes. Yes. Yeah. So there is no closure property with respect to the Moore-Penrose inverse and groupings. Yeah, that's the thing. So this is new. So if you have on the other hand, if you have a non-singular matrix whose inverse is non-positive, then again it's a Q0 matrix. See, this has no relation to the previous theorem. Then again it's a Q0 matrix, and again the proof is almost there. Any Q for which LCP A comma Q is feasible must satisfy this equation. So Ax plus Q, you are asking for an X, you are asking for a non-negative X that satisfies Ax plus Q equals 0. And that's immediate. Justification as to why a non-singular matrix with the non-positive inverse is a Q0 matrix. This is not true for the Moore-Penrose inverse. Again, if A dagger is non-positive, it doesn't mean that A is a Q0 matrix. This is the example. This is different from the previous one. Now, for the group inverse, we don't know. There is no such counterexample for the group inverse that I have been able to find. But it appears as though if the group inverse has rank n-1, and if the group inverse is non-positive, then the matrix A must be a Q0 matrix. It appears to be. I haven't verified. This is still something that is ongoing. I'll now go from the usual cone to Sn plus. From the usual cone to Sn plus. So I'm looking at the semi-definite linear complementarity problem. So you look at Sn, the space of all real symmetric matrices of order n, then Sn plus is the cone of positive semi-definite matrices. I look at SDLCP, for an operator L. So L is a linear operator. Q is given in Sn. The question is, does there exist a positive semi-definite matrix X such that Lx plus Q is positive semi-definite and that the dot product is 0? So the inner product there is the trace inner product. And so this is the semi-definite linear complementarity problem. Now one can ask questions like whether an operator has a P property or a Q property, etc. When does the problem have a solution, etc. It's easy to formulate what is a Q property. LCP has a solution for all Q. Then it's a Q property. Q naught property is feasibility implies solubility. The moment you have a feasible matrix, you must be able to find a matrix is also satisfies the complementarity condition. So there is nothing, just the extension goes through. Now in this framework, there are three famous operators. One is a Lyapunov operator. The other one is a Stein operator. The third one is a multiplicative transformation of the multiplicative operator. So I'm asking now some questions regarding these three operators. The first question that so what is a Lyapunov operator? For the Lyapunov operator, so I'm giving the definition there. The result of Ekambram and Mohan is not true for the Lyapunov operator. Meaning what? I have an example of a Lyapunov operator which satisfies the Q naught property, but it doesn't come from Ekambram-Mohan's theorem because it's not true. Ekambram-Mohan theorem does not hold. So look at the Lyapunov operator. This is the Lyapunov operator. LA of X is AX plus XA transpose. And for this matrix A, this is the adjoint operator. The nullity is 1. In fact, the null spaces of LA as well as LA star are spanned by positive definite operators. This problem is feasible.
Are you working on this?
Yeah.
So is it possible to get instead of 2 by 2, 3 by 3?
3 by 3, yeah. It's
So
3 by 3 is much more difficult. 2 by 2 itself is
2 by 2 problem that many of the things may not go through.
Yeah. Yeah. 3 by 3 is still more difficult, but I'll try. Yeah. So this is an example of an operator which satisfies Ekambram-Mohan theorem, but it is not a Q naught operator. So even Q by 2, it does so much effort to show it does not have a complementarity property. It doesn't have a complementary solution. However, something that's may appear very strange because I'm just considering particular cases. Something that's true is that if A square equal to minus I, if A inverse is negative A, then LA is a Q naught operator. This has some context, but I'm not sure if I have the time for it. This A square equal to minus I has some context. For this A square equal to minus I, for instance, the Lyapunov operator turns out to be a singular M operator. For the case when A square equal to minus I, the Lyapunov operator is a singular M operator. For the singular M operator, we were able to get a result similar to the singular irreducible M matrix. And so this has some history, but it's not negative. Something does not have Q naught property. Instead of that, I have some result where the operator has the Q naught property. Let's look at another result for Q naught matrices. For Q matrices, a non-negative matrix is a Q matrix if and only if all the diagonals are positive. That's a result for Q matrix, necessary sufficient condition for a non-negative matrix to be a Q matrix. For a Q naught matrix, the statement is that if it is non-negative, then it is Q naught if and only if corresponding to a diagonal which is 0, that entire row must be 0. If that condition is satisfied for the non-negative matrix A, then it's a Q naught matrix. The most typical example of a non-negative operator is in the space of Sn is the multiplicative operator. This MAX is AX A transpose. This is a positive operator because it leaves the cone Sn plus invariant. Trivially, this is a positive operator. Does this positive operator have the Q naught property? That's the question. The answer is there's a negative result. It doesn't have Q naught property if rank of A is 1. This does not have Q naught property if the rank of A is 1. It looks like true for rank of A equal to 2 also, but this much is sure.
Rank of A greater than equal.
Rank of A equals 2. Yeah, the same theorem applies when rank of A equals 2. But higher ranks, it's not clear. So that's the case with this positive operator. That's how I'm enjoying my math. So, Benman Clemens, Bhagavad Gita of non-negative matrices. The second paper is where we explored this singular irreducible M matrix property for the Lyapunov and the Stein transformation. This appeared in linear multilinear algebra. Gowda Song, Gowda TP. TP is our complementarity group. Gowda Song, Gowda TP. These two papers, they considered the semi-definite complementarity problem. In my opinion, these two important main results are beautiful results, extending the invertible M matrix theorem to the Lyapunov transformation and the Stein transformation. And Murthy, myself, and Sushmita, my former student, this is where we proved that this non-positive matrix must be a Q naught matrix. Thank you.
Any more questions?
So it is good that you are looking at Q naught matrices again. So it is one, these are the matrix classes where people have not worked for, after I think last 10 years, people are not working, no, that, but there are lots of hard problems are there. So
yeah, so my interest is in this non-positivity kind of thing.
And it will be interesting that if you get some results, no, which will help in recognizing Q and Q naught matrices, so that in order to test, no, that students find it very hard to check a matrix whether it is a Q or Q naught.
Yeah, and these operators are all very difficult to work with.
Difficult to learn, yeah. So it's nice. I mean, you have a big group, so you can explore.
Thank you.
Still time. So any questions from the audience? No? You have questions? Okay, if not, then let's thank the speaker.
Thank you, sir. We also thank our chairperson, Rafiqul Alam, sir. So this completes the invited talk session.
There's just one little thing left. Yes. My shawl.
And tomorrow,
I have to wait till tomorrow.
yeah, he's the chairperson for tomorrow's phone session. Then. So now we move for tea break up to 4:35. So from 4:35 to 8:45, we have contributory talks. Sorry, 6:45. Thank you. Yeah, sorry. Room is academic block 3. Who attended for workshop, they know. It is the board is academic block 3, but they will also call it as NLH. So it will be in the first floor, and room numbers are already shared with you, and also they have been pasted below. It will be 202, 203, 204, 205. Yeah, thank you.
So I'm happy that you are continuing with this, no, that our community itself has become very.
Yeah, contributed to us, it is opposite to the photo session where we took, that is academic block 4, opposite to that is academic block 3, first floor.
There are how many students?
I have a question.
Yes, yes, please.
Here we go.
Yes, yes.
Okay.
Of course.
The slides which you gave, can I share with students?
I request the Manipal scholars to escort the dignitaries to the NLH.
Thank you.
Question. Yes, please.
ಅಷ್ಟೇ ಮುಗೀತು. ಹೌದು. ಸರ್ಟಿಫಿಕೇಟ್ ಎಂತ ಆಯ್ತು? ಧನ್ಯ ಮ್ಯಾಮ್ ಎಲ್ಲ ಸರ್ ಕೆಳಗಿದ್ದಾರ. ಇಬ್ರಿಗೇನೋ ಸರ್ಟಿಫಿಕೇಟ್ ಕೊಡ್ಬೇಕಲ್ಲ? ಯಾರ್ಯಾರು ಹೋಗ್ತಿರೋದು ಈಗ? ಇಬ್ರಲ್ಲ, ಮೂರು, ಲೀನಾ, ಸಸ್ಮಿತಾ ಮತ್ತೊಬ್ರು ಸುಬ್ರಹ್ಮಣ್ಯಂ. ಅವರು ಹೋಗ್ತಾರ? ಶ್ರೀರಾಮಕೃಷ್ಣ ಸುಬ್ರಹ್ಮಣ್ಯಂ.